Hello, everyone. My name is S.Panda. I'm currently a postdoctoral fellow at the National Astrophysical Laboratory in Brazil. I thank the organizers for giving me this opportunity to present the recent highlights of our software development to study and predict the emission line delays using photometric reverberation mapping data from the upcoming Vera Rubin Observatory's LSST. This work is a key aspect of the in-kind contribution on behalf of the Polish LSST consortium. This is a directable software that would be accessible through the Aegean Science Collaboration. We have prepared a numerical code which simulates the efficiency of the time delay measurements with LSST. The code includes the simulated light curves contaminated by strong emission lines, H-beta, magnesium-2, and carbon-4, iron-2 pseudo-continuum in the optical and UV band, and the starlight contribution. The code identifies the optimum bands representing the continuum and representing the dominant line plus continuum contribution for a given redshift and recovers the time delay under the sampling implied by the specific LSST cadence simulations. This allows to simulate the accuracy of the recovery of the broad emission line delays. In this way, we also optimize the future modeling effort by the choice of prospective sources at each stage of the duration of the project. The code takes into consideration several key parameters to produce these light curves, namely the campaign duration of the instrument, which is 10 years, the number of visits per photometric band, which is obtained from the cadence simulations, the photometric accuracy, which is now as the point varies between 0.1% to 10% of the actual magnitude of the photometric band, the black hole mass distribution. Here we are showing the results for a representative black hole mass of 10 to the power 8 solar masses, but in the end, the eventual program will incorporate the full distribution from, for example, the SDSS quasar catalog. We also incorporate the luminosity distributions. The current results shown here are for two representative cases of Aegean luminosity at 3000 angstroms, which is 10 to the power 44.7 and 10 to the power 45.7 ergs per second. We incorporate a full redshift distribution, and the line equivalent widths and full width half maximums are consistent with the SDSS GR14 quasar catalog. We also incorporate frequency breaks and slopes of the underlying power spectrum, which is then used to derive the timescale and variability levels of the light curve using the prescriptions from Timmer and Koenig 1995. And of course, we use the sky coordinates for the simulated source using a randomized search over the sky maps produced by the LSST cadence simulations. We then calculate the total contamination to all photometric bands for a given redshift and source properties. This is done by folding the spectrum shifted to the observed frame with the profiles of the LSST filter responses as shown here in figure 1. We select two channels currently for the time delay measurements, one strongly contaminated by any of these lines, and one which is not contaminated, but still close to the selected contaminated channel, which then is used as the continuum channel. The model light curves are generated using the two dense light curves using the simulated cadence in two adjacent channels. Finally, we determine the time delay using chi-square method. The errors in the delay measurements in both cases is set by the dispersion in delay measurements obtained from 100 statistical realizations of the initial stochastic light curves. Here we are presenting two results of the two different luminosity cases. The upper one is for the low luminosity case, 10 to the power 44.7. The lower one is for the higher luminosity case, 10 to the power 45.7. The black line over here shows the adopted recovery time delay according to Bench et al. 2013 relation of the standard radius luminosity, while the underlying error bars data point are from the simulations. The code is modular and allows to incorporate other time lag techniques such as Javelin, ICCF, ZDCF, and so on and so forth. Our code at present is used as a predictive tool to recover the success rate. That is, for how many quasars can we recover the time lags and estimate their BLR sizes. Upon first light of LSST, Our code will act also to estimate the time lags for real quasars. Finally, the code development is still in progress, and these are only first results that we show here in this poster. We are working towards further improvements, primarily, for example, assessing the performances of existing time lag methodologies and determining the success rates for time lag recoveries based on realistic quasar number counts as a function of quasar magnitudes and redshift distributions expected to be recovered from the survey. Thank you.